All right, so welcome everybody to the Internet 2 National Research Platform Engagement webinar Zoom session. Today we have one of my favorite people, Dan Schmiedt from Clemson, giving us his presentation on the life of a packet. He's at Clemson University, and I will just hand it right over because I'd rather hear him than me. Thank you, Dan.
Okay, thanks, Dana, and hello, everybody. I'm blown away. Dana didn't tell me that I'd have 200 people watching me, so we'll try not to be nervous, but I can pretend like there's only a couple of you, I guess. So first off, I'm at home on a crappy AT&T DSL connection, so if I slow down and disappear every once in a while, I'll generally be back. My name is Dan. I'm the Director of Network Services and Telecom at Clemson University. So my team is responsible for making the internet and the telephones and everything that has to do with those things work. We handle everything from splicing fiber all the way up to running the big routers that talk BGP. And we also run the state research and education network, which we call CLIGHT. I started at Clemson as a student employee in the early 90s, and I thought that networking was really cool, and so I started kind of hanging around the network services office, even though my job was to work in the computer labs. And eventually they asked if maybe I wanted to come work in network services, and I did. And I was blown away with how much I did not know, and I figured, like I did in my other student job, that if they ever figured out what I didn't know, I'd get fired. So I just set forth to always try to be learning. And I'm still kind of that way. And I've worked my way up from being a network engineer junior to being the chief network engineer. And then they kept kind of getting the wrong people to be in charge of the team. So I kind of had to go be in charge of the team, even though I would really probably rather be a network engineer. So the story I think you saw in the abstract is that at one point I left Clemson and I went to go work what I thought was my dream job at Cisco Systems. And for that interview, they said, well, you have a cool, impressive looking resume, but we don't care about that. What I want you to do is get up to that whiteboard up there and tell us how a packet gets from this computer right here to a web server out on the internet. And don't leave out any steps. That was the whole interview. And I went up there and lo and behold, I was able to kind of reason through it. And I got the job, even though I didn't stay at Cisco very long. I came back to Clemson with a really good understanding of some things that I wanted to work on. And also one of the things that I came to think of was that if I wanted more and better network engineers on my team, I needed to train them. I needed to have a way to explain networking. And so what it came back to was that interview. And let's just take a whiteboard and let's make a packet on our computer and let's put it out on the internet and understand how it all works. And so as I worked as a network engineer, I would always draw out a computer and then the physical network devices that were in the way, and then just reason out what is the packet doing all the way through there. And then you can dig in and always figure out what's going on. So anytime I think of a network problem, I start drawing a picture. So Dana was telling me that you guys get cross-eyed when people start talking to you about layer 2 and layer 3 and other networky kinds of things. And what I'd like to do is just break down networking on the whiteboard. And I think you'll understand what we're talking about when you hear about those things. So this is meant to be interactive. I would like for all of you to, I don't know how this is going to work with 200 people in the room, but we'll try it. I want you to kind of jump to some conclusions and follow me along and help me reason through how things work. Also keep in mind, I'm not a network engineer anymore. I mostly write emails and wave my hands around all day long. And every time I do this, I wonder if I still remember how to do it. So I may need some help from some of you on on some things, and if you know the answer, I'd appreciate you helping me out. So again, participate if you can, wave your arms around, nod, anything like that really helps me understand that I'm getting through to you. So let's try this. So if we have a computer here, and there's a person here using this computer, and that computer has got, let's say that it has a wire coming out of the back of it, and it goes to a jack on the wall. And the jack on the wall threads through all kinds of other walls and stuff like that, and winds up in an equipment closet somewhere down the hall from where that computer is. And in that equipment closet, there may be a number of switches. A switch is a network device. It looks kind of like a metal pizza box with a whole bunch of RJ45 plugs on the front of it. And usually at any place that usually they're 24, 48 port switches. Sometimes they're big refrigerator sized chassis looking things. It all depends on the philosophy of your networking department. But you'll have some kind of a switch there, and we call that an access switch. And they just take the connections from the computers, or nowadays, you might connect a wireless access point to these things. And at Clemson, we still have a jack on the wall, and we plug the access point into the jack on the wall and take that back to one of the access layer switches. These access layer switches, generally inside of a building, might be aggregated by a switch or several switches, which is just usually a beefier version of the same thing. And maybe they use two for redundancy to minimize the points of failure. And then maybe you might have some campus aggregation switches that generally might actually be big refrigerator sized things. And you might have something like this going on where we have an uplink to the two. This might be one, at Clemson, we have a building called Strode, and we have a building called Riggs. And all of our buildings have got fiber that goes from each building to those two buildings, and that's where we aggregate all of the campus network together. And then you might go from those to something like a data center. In our case, we have two data centers. We have one at Pool Hall, and we have one at a building we call the Information Technology Center. And these might aggregate, in our case, servers. There might be some high performance computing in there, something like that. We sort of mirror the stuff between our two data centers. Then we might have something like the evil firewall. Make some bricks here. And the firewall might connect back to something that we call a border router. Could have multiples. And this border router connects to the outside network. So we'll just say at our place, we run a regional network called C-Light. In Clemson, although we run it, we treat ourselves just like a customer. Let's see. We have one in Anderson, which is a town near us, and another one in Clemson. And then C-Light has various upstreams, and we'll just abstract all these upstreams as clouds. We'll talk more about why we do that later. But we might go through any number of different clouds that might be connected in various ways. And let's say eventually we're winding up at Google's cloud. And somewhere in there would be a server that happens to be answering www.google.com. And let's just say that the point of this whole exercise is that we want to see the packet get from this computer here all the way to this thing that's answering over at www.google.com. And we want to understand what happens to that packet as it traverses that network path. Is that making sense? Can I get some thumbs up or something like this? Am I making sense to everybody so far? Okay. So all we want to do, great. All we want to do is see a packet get formed that tells this web server over here at www.google.com to send us Google's homepage. That's all we want. So in order to do that, we have to get an HTTP GET request all the way over to that website. So let's build ourselves a packet. Let's see if we can do that. I guess I should mention that a packet is just like you might imagine the word implies. It's like an envelope that contains information, and it could be multiple envelopes inside of one another. But ultimately, somewhere at the end of the final envelope is a message. And in our case, this message is going to be this HTTP 1.1 get / something like that. That's the command that's got to get to the web server. So we know that that's got to be in there. So the packet is nothing but a string of ones and zeros. That's all it is. And it's arranged in a particular order. The end of the packet contains the information that we want to get to the other side. All the stuff at the beginning are called headers. Just like when you're going to put that package into a mailbox, it's going to have your to address on it, and it's going to have a from address on it. Packets have source and destination addresses. But this part, all of this part up here, this part that I just highlighted there, those are all of the packet headers. And the network gear, what it does is it reads those headers. So the question is how do we put this whole packet together, and what order does the information go in? Let's see if we can make a little sense about that. We'll spend a little bit of time here building a packet before we can actually put one out. This is actually one of the hardest things to get down is how is the packet built? How does it come together? Have we ever heard of this thing called the OSI model? Does that ring any bells with any people? Let's talk about why that is. OSI model. It's a 7-layer model. And this was a model, I should know the history of it better than I do, but this is the model that ultimately made the internet that we're using today a thing. Prior to the advent of the internet as we know it, there were various companies that made computers that made computer networks, and they figured out the format they were going to put the data in and how they were going to send the data, and they did it in their own proprietary way. And the problem was that anytime you wanted to interconnect two different systems together, it usually didn't work. So we had to find a way to abstract different parts of the network away, so that if I wanted to run my network over fiber, if I wanted to run my network over copper, if I wanted to run my network over smoke signals, there could be a common way that we could interface between those different physical infrastructures to connect. And it went all the way up the stack like this. So at layer 1 down here, this is the physical layer. And that is the physical medium on which a network operates. I've already told you some examples like fiber. There's twisted pair. It could be wireless is a big physical medium we use a lot these days. You could also figure out how to send IP packets over smoke signals if you really wanted to. So this is stuff like fiber, copper, wireless, and so on. The next network layer is called the data link layer. And this is how we get packets from one point to another point, just from my computer right here to this network switch right here. That's the only thing that the data link worries about. It has no clue how to get any further. It's just the single link. Can somebody shout out a very common data link layer protocol that we use a lot today? Ethernet, I see it in the chat. Perfect. Ethernet is a great example. There are other ones. Back in the day, there was Token Ring. There used to also be, there, I see James Deaton there. There was also ATM, there's, I don't know, Sonnet. The list goes on, but these days, Ethernet is kind of the king. InfiniBand, there you go, that's a good example, excellent. The next layer here is called the network layer. And this is a collection of protocols that worries about how you send data across the whole network. So that whole picture we just drew up there, that's what this layer concerns itself with, is what are, you know, how do we not only get from just one point to the next, but how do we get all the way to the end of a network? FDDI, good example, Oliver, yep. So anybody have any guesses on some network layer protocols we might be familiar with? IP, exactly, IP. What about, we say IP, yeah, TCPs, we'll get there. It's not TCP, not ICMP. So IP is a good network layer protocol, and it so happens that there are actually two, right? We have IP version 4 and we have IP version 6. Basically the same protocols. One has a whole lot more address space available, but they're technically two different network layer protocols. Back in the day, there was also IPX, if you remember Novell, and there's AppleTalk. When I first started in network services, we configured on our routers IP version 4, IPX, and AppleTalk. And these days, pretty much all we run is IPv4 and IPv6. The next layer is the transport layer. And this layer is responsible for how you move data, how you either reliably or don't reliably move the data across there. Somebody mentioned TCP. This is where TCP fits in. TCP is a layer 4 protocol. Somebody's mentioning TCP/UDP. UDP is another layer 4 protocol. So TCP has a method that it uses a three-way handshake to ensure that every bit of information that goes across is actually correct. And UDP has no such method. Anybody care to guess what layer 4 you're probably using to listen to me right now? You think that's TCP or UDP? Right, it is UDP. And UDP is oftentimes considered unreliable. Why would we be using an unreliable protocol? Why would we do that? Wouldn't we want to make sure that we got all the packets? So, right, less latency, and well, this is live. So like if my junky internet connection drops a few packets, you can't rewind and go get them. You're just going to have to fill in with some noise and move on. It's just like if you're listening to a radio broadcast and a crash of static comes through. Well, it's too bad. You just missed that part of it. That's the way it goes. So when we're talking about real-time things, that's when we use protocols like UDP. And when we're sending data, like a file that we care about being 100% correct, we're going to use TCP. And there are other layer 4 protocols as well, but TCP and UDP are the big ones. So then we get into layers that, as a network engineer, I kind of usually have to remind myself what they actually are. So I won't spend much time on these except to tell you that they're here, and we'll give an example. So we have the session layer, the presentation layer, and the application layer. So let's put all this together and see if we can understand why we just spent a couple minutes doing this. So let's just say that we're running a web browser called Firefox that is rendering to us HTML that is being run over HTTP, the Hypertext Transfer Protocol. Firefox over HTML, showing us HTML over HTTP, over TCP, over IPv4, over Ethernet, over, we'll say, a copper cable. And that's how the whole stack fits together. So you can use different applications, you could use different things, but this is how the OSI model fits it all together. And you can see that I could use my same Firefox web browser to make things work over IPv6, or I could use my same internet connection to, you know, over, if I wanted to use token ring, I'm sure we could cobble up some way to make that work at layer 2. If I wanted to use wireless, that's just a different physical layer protocol, and they all fit together in the same ways. So why did we were building a packet, right? And all of a sudden we switched to this thing. Well, guess what order the stuff comes in the packet, right? So we have, this is layer 5. So yeah, let's see if I can get this right. So now we just have to fill in some stuff. We have a destination and a source. Destination and a source. And in this case, we have, this is over port 80, let's just say. So the packet is put in order of this model. So we start physical layer, it's physical. There's nothing you can do about it. So the packet actually starts usually at layer 2. And the very first thing in there is going to be the destination address. Where is it going? And it's put in that order because as this packet leaves this computer, this packet is going to be pushed down the wire in this direction, with this part being read first. So why would we do that? Anybody want to guess why wouldn't we send the the HTTP GET request first and then put all the stuff behind it, right? You can fill in the blank and imagine that it might be that because this switch right here it doesn't care, it doesn't even know what HTML is. It doesn't know it, but it does understand how to read layer 2 addresses. So in our case, these layer 2 addresses are called Ethernet addresses, often called MAC addresses. So we've got to fill in, we've got some stuff to fill in. Let's say, so destination, that might be a little hard to figure out what we're going to put there, so we'll ignore that for right now. Source Ethernet address, where does that come from? did a person assign that to this computer, or anybody guess where? That's right. It came from the manufacturer of the Ethernet card. And it's some 48-bit address represented in hexadecimal. And it usually looks like AA, BB, something like that. And there's 3 more sets of numbers there. Let's see if I can make this bigger so I can draw a little bit better. All right, destination MAC address, let's think about that one. All right, layer 3, we look over here to our model, and we remember that that's going to be IP, probably IPv4 or IPv6. Let's just use IPv4 for this demonstration. So destination IP address. We know we were going to www.google.com. How would we turn that into an IP address? What is the mechanism that does that? DNS, exactly right. So we would use a protocol, and in networking, when I say the word protocol, that's just a standard agreed upon way of doing things. So in networking and in computing, we have a whole set of things called RFCs, a request for comments, which is where people who had an idea about the way they wanted to do something on a network sat down and wrote out a way to do this, and that way is called a protocol. So the protocol that we want to use to convert www.google.com into an IP address is called the DNS, or the domain name system. So we use the DNS protocol to send packets out and say, hey, what's the IP address for www.google.com? And let's just say you go out there and it comes back as 64.28.16.2. Somebody was being quick, they could go jump on a terminal session and do an NS lookup or a dig and get the IP address. And if I'm in person, I usually have somebody do that, but that might be a little much here. Destination IP address. Where did that come from? Any clues? Anybody have any clues as to where the destination IP address, or I'm sorry, yeah, well, I got those backwards. Sorry here. Bear with me. So 64.28.16.2 and source IP address. I'm sorry for that. Anybody have any clues where your computer gets its IP address from? DHCP or static? Very good. DHCP is another protocol called the Dynamic Host Configuration Protocol. It is the method through which IPv4 hosts get their IP addresses normally. They can also be assigned statically. DHCP hasn't been around always. That's correct. Or if you're right, IPv6 can be DHCP, or it can be assigned through an autoconf protocol. But if we're thinking about IPv4, there's this thing called DHCP that gets us the IP address. Most of us, probably that's how we got the address of the computer we're using right now. But that hasn't always existed. And my first job at Clemson was to answer the phone at Network Services and say, Network Services, this is Dan. And somebody on the other end would say, hey, Dan, this is Ken over in biology. How you doing, bud? And I'd say, oh, I'm doing pretty good. And he'd say, hey, listen, we just got a new computer and I need one of them IP addresses. And I'd say, all right. And I'd pull up my VAX terminal and get on there and pull up our database and get him the next available IP address. And I would give it to him. And that's the way we did every computer until 1998 when the DHCP protocol was invented. And then I got all excited because I didn't like that part of my job. And I set up a DHCP server under my desk that handed out the IP address. Let's just say, for our case, so that we don't have to dig into how DHCP works, we'll just say that I got an IP address that was statically assigned, 130.127.4.28. And let's just say that I got some other information as well. When I got that IP address, I got a default gateway, and that would be 130.127.4.1, and I got a subnet mask that was 255.255.255.0, and I got a DNS server of 130.127.8.8. We'll just write all that stuff down and we'll come back to it. So the only thing, we have our packet almost completely built now, and the only thing we have to do is figure out the destination MAC address. So now how in the heck are we going to find out what the Ethernet address is of that thing way over there at Google? And if we think back and remember that we talked about, we're talking about layer 2, and remembering that layer 2 only cares about how we get from one link to the other end of that link, and it actually goes to here. This box right here up at the top of the screen there, that is my default gateway, and that is the router for my network. And so my computer has to determine that 64.28.6.2, which is the destination IP address of www.google.com, it needs to figure out that that's not on the local network, and then it has to say, if it's not on the local network, I need to send it to my default gateway. So my question for you then is that if we know as human beings probably that unless we work at Google, www.google.com is not likely to be on the same network that I'm in. But I'm a computer. If I'm this computer right here, how do I know that it's not there? What's the logical method that the computer uses to figure that out? Anybody know? Somebody said subnet mask. That's exactly right. So an IP address is really, it's really a set of ones and zeros. In the case of IPv4, it is, anybody know how many bits are in an IPv4 address? 32. That's exactly right. There are 32 bits, and we represent it in a dotted quad. So each one of these numbers here represents 8 bits. So for a total of 32 bits. And the way you convert to binary is you use the powers of 2, and you might figure out that 130.127.4.28, which is my IP address, comes out to 1, 2, 3, 4, 5, 6, 7. Let's see, 1, 2, 3, 4, 5, and then 28, 0, 0, 0, 1, 1, 1, 0, 0, yeah. So 130.127.4.28. And each one of these positions, this is the 128-bit position, 64, 32, 16. You can look up how to do binary math, and you can. It's fairly simple once you dig through a couple of them. But this subnet mask that we got right here, 3 255s and a 0. If we convert that to binary, look, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. What this does is it provides, the computer then does a logical AND. That means that if both things are 1, the answer is true. It does that, and it figures out whether you're on the same network or not as the thing you're trying to get to. In this case, as humans, we can see that 64.28.6 is not the same thing in any way, shape, or form as 130.127.4.28. So we know that we're going to have to send this packet to the default gateway. What would happen if www.google.com did happen to be hanging off right here? Then we would put the actual MAC address of that, the layer 2 address of that system in this portion of the header. In this case, we figured out that it's not. So we're going to put our packet in here. And let's just say that our destination MAC address, just to simplify things, is the letter D. And it would normally be some big 48-bit thing, but we're just going to say it's D. And that happens to be right here, right there. So we have a complete packet now, and now we're ready to send it onto the network. So our computer takes this packet, sends it out, and it gets to this access layer switch right here. And this access layer switch, let's say it was just turned on. It is completely empty. It's never seen a single packet before, and this happens to be the very first packet that it sees. So the question is, what does it do with it? It's the very first packet it's ever seen. Does anybody have any clue what it does? It does learn the source MAC because it heard me send the packet, so it knows that I am, let's just say I'm plugged into port 2 over here. So it knows that much, but this MAC address D we finally put in our packet. Where does it send it? How does it figure? Somebody said all ports. That's right. So it knows it's not on the port that I sent it from, right? So it sends that packet out every single port on the switch. It just forwards it to all the packets. It doesn't, you could consider a broadcast, but it's really just forwarding to all the ports. This switch has got to move this packet. The switch doesn't, this is a layer 2 device, meaning that it only understands how to read this much. It can, basically it can read destination and source MAC addresses, and that's about all it does. Knows nothing else, and it has to move the packet. Does not have a choice. It can't decide, no, I don't know what to do, I'm just not gonna move it. It got to move it somewhere. If it doesn't have a specific entry, I've said a word. This switch maintains a table on it. This table contains the ports and the MAC addresses that it knows are on each port. So in my case, it knew that it heard me. I'll just write me there on port 2. Since it didn't know anything else, it sent my little packet with the HTTP GET /request. It sent it out all the ports. And that'll definitely get it to where it's going, except it doesn't send it down the port that it heard it from. Another word for switch is a learning bridge. So that was actually the original term used, meaning that it learns MAC addresses and it keeps a table. And this table gets flushed out every 5 minutes usually. So that packet then moved on. When would it learn when would it learn that the router was plugged in on port 6 there? When would it learn that? Any clues? Maybe when the return traffic starts coming back. That's right, exactly right. So then it would populate that and it would learn that on port 6 was D, which is the default gateway. So now this packet has moved through the switch and into this first device, this next device here. This is a router. Another word for a router is a layer 3 switch, which, as the term might imply, it can not only read layer 2, but it can also read layer 3. And so the router has another table inside of it. So the switch has got this MAC address table. On a router, any idea what the table is typically called inside of a router? Any idea? Routing table, exactly. What entries do you suppose might be in this routing table? I saw your question. We'll answer about switches in just a second. Maybe prefix and next hop. So that might be like 130.127.8.0. Next hop is 130.127.3.2, 130.127.4.0, and our next hop 130.127.3.20, let's just say. So a router maintains a routing table of, let's say that this is this 130.127.3.2, and this one is this other one that I mentioned there. And the router takes a look at, so if we said, remember back here we said that subnet mask was 3 255s and a 0. So that tells us that the first 24 bits, these ones right here, these first 24 bits are the part of the packet, part of the network address that represents a network. And the last 8 bits represent hosts on that network. The first part of the IP address is called the prefix, and that's the part that identifies that portion of the address as a network, and the next part is the host. So the router keeps track of, let's see, router keeps track of prefixes and what is the direction you would get there. And they might have a default route of something. Let's just something like that. Meaning if it doesn't know where to send it, then it sends it there. Question for everyone. How did the router get these routes? Where did they come from? These entries that it has in its routing table. Where did those routes come from? Routing protocols are manually entered, exactly correct. So as a network administrator, I could just statically, that means get on the router and say, hey, to get to this network, it's out this way. To get to this network, it's over here. To get to this network, it's over here. And you could certainly do that. It would be a complicated way to run a network. Instead of doing that, we have these things called routing protocols. Remembering that protocols are just a way of doing something. A routing protocol is just a way of describing to a router how to get to various networks. So there are interior gateway protocols and there are exterior gateway protocols. Gateway just meaning router. You might hear of some of these like OSPF, Open Shortest Path First. The original routing protocol was called RIP, Routing Information Protocol. There's proprietary ones like Cisco's EIGRP. There's IS-IS. And the only EGP that we use today is a protocol called BGP, or Border Gateway Protocol. And so inside of a network, that's everything in this circle here, typically would run an IGP like OSPF or something like that, to learn. All the routers say, hey, I'm a router and I know how to get to all these different networks. And they're like, okay, well, I'm a router too, and I know how to get to these networks, and they build their tables. BGP is used that on the internet. And big difference between the interior gateway protocols and outside and in EGP is the difference in trust. So inside of my network, my routers generally all trust each other. I configured them all, I do that. But when I'm setting up a connection between me and some service provider, I don't trust them any farther than I can throw them, and they definitely don't trust me at all. So I pay them money and I say, I'm gonna tell you about these networks, and they verify that I own those networks. And then they're like, okay, I see you own this network and you've given us this big sum of money. I will carry your routes, and I will give you the whole internet or some portion of the internet. Or if I'm a research and education network, I will tell you about how to get to all of the schools and universities and other things that are directly connected to me. So this border router right here would maintain information about both. So let's put all this together. We are running out of time here. Let's put all this together and run, and let's be the packet, and let's go through the network and see if we can make sense out of this. Okay, so we built our packet, put together in the order of the layers. The packet comes, let's zoom in here. Packet comes into the access layer switch. The access layer switch reads the destination MAC address. If it finds it in its MAC address table, it sends it out that port. If it doesn't find it in its MAC address table, it forwards it out all the ports except for the one it came in on. Then it winds up at and there could be multiple switches in the way. Somebody said, why would you use switches? And the answer is because switches are cheap. And they can constrain traffic. In the old days, we used hubs, which just every packet that went in just went out all the ports every time. Switches constrain traffic fairly well, and they're inexpensive. But they don't scale. You couldn't run a whole internet with nothing but layer 2. You would have to have upper layer protocols. Then it gets to our default gateway. Our default gateway looks and says, it's going to 64.28.6.2, and it looks where it looks in its routing table, and it says, I don't have that in any of my prefix lists right here in my routing table. So I'm going to send it to my default route, which in this case might be this router right here, that Strode router. And then Strode is going to take a look at that, and that router might have a bigger routing table, or it might not. It might just have another default route in there, and it would send it on down the line. Now, interesting question for you. So this packet is passing through this router. Is anything changing inside the packet? Does anything have to change? Does any of the layer 3 stuff have to change? No, it doesn't, because it's always going to be headed to the same destination. And it's always going to be coming from the same source. But layer 2, this is going to change every time it goes through a router, right? Because now what the router has to do is change the destination MAC address to that MAC address of the next hop. So every time the packet moves through a router, it rewrites this layer 2 portion of the header. Every single time it does that. It moves it through there. And then we get to this firewall that maybe some of you guys have run into some issues with firewalls. What does a firewall do? Does a firewall, what portions of a packet does a firewall look at? The answer is that the firewall is typically capable of looking all the way up to layer 7. I could build a firewall rule that says anything that contains the word Dan Schmiedt, drop that packet. you could do that, right? So it's just a layer 7 aware network device that is capable of keeping track of a huge number of rules that might say those things. It also maintains state, meaning it keeps track of traffic going out and then what would be the corresponding traffic that's coming back in. So typically we use these devices to, or our security departments use these devices to apply security rules to our network. Then it gets to the border router, and the border router maintains information about externally connected things. So it might have multiple ways to get to google.com. It might go out through a commercial service provider, and it might go through a research and education network. So let's see, I see Brian's got a question here. Does this overriding imply that Google's responsible for traverse the same route in reverse? Good question. No, not necessarily. It could go in a completely different direction in the way back. Inside of each one of these clouds, likely they're running an interior gateway routing protocol, just like we are. You could think of what's going on in each one of these clouds as the same thing I just drew inside of Clemson's network there. Same sort of thing could be going on inside of there. There's going to be layer 2 switches. There's going to be routers doing layer 3. There could be firewalls, all kinds of stuff, but that's localized. And since I don't care, I just need for them to carry my packets. I don't care how they do that. And so BGP allows us to abstract that out. And so I can just see what these, anybody know these clouds? What's a name for them that we use in the networking world? Anybody know? Autonomous systems, exactly right. AS, and every AS typically has a number. Clemson's is 12148. If you can use the BGP protocol to figure out how you want to prefer traffic to go out, and you can also cause it to manipulate how your traffic might come back. But it's a lot harder to control the returning traffic than it is the outgoing traffic. And across through these clouds, if you just imagine what we described going on inside of our local network, where we have layer 2 switches that are either finding MAC addresses in their MAC address table, or they're forwarding out all the ports, and layer 3 routers that are reading source destination IP addresses and determining what the next hop is. And they're just doing that over and over again. So I said that a switch cannot drop a packet. It has to forward it somewhere. A router, does a router have to forward every packet? What does a router do if it does not find an entry in its routing table, and maybe it does not have a default gateway? Anybody know? Just a guess? It drops the packet. So another word for the internet in routing land, yes, is the DFZ, or the default free zone, meaning that routers that are out there on the internet, they either know about how to get to something or it does not exist. If it does not exist, we're not going to forward that packet. We don't need packets going around that don't go anywhere. So we drop them. So on the network that I run at Clemson, we generally have default routes on all the routers. Those routers are going to send the packets on. But out on the internet, if there's not a route to it, the router is going to say nope. And it's going to send a message back via a protocol called ICMP, or the Internet Control Messaging Protocol, and say, hey man, I'm sorry, there was no route to host. That's what happens. So let's talk about what's a tool we can use to figure out how traffic goes through a network at layer 3. Anybody know? Maybe you've used this tool before. Traceroute. So I can say traceroute www.google.com, and I can see how that packet gets there. Question, how does that work? Anybody know? So every packet that goes out on the internet, one of the fields in there is a time to live. That means how many router hops can this packet go through before it needs to die? Like, we wouldn't want packets infinitely looping around out in the internet. That would not be scalable. So at some point, the packet has to die. And so routers are configured that every time they do that layer 2 rewrite, they decrement the time to live value, which starts, I don't know what it starts at, but somewhere maybe, I don't know, 30, something like that. And it decrements that count. And when the count gets to 0, it kills the packet, and it sends a message back to where the packet came from and says, hey, I'm sorry, man, I had to kill your packet. Its TTL was exceeded. So all Traceroute does is it sends out a packet to the destination with a TTL of 0 initially, and the first router gets it and it's like, nope, sorry, I killed it. Well, when that router answered back with that ICMP TTL exceeded, it says, hey, and I learned who the router was. And then I send one out with a TTL of 1, and it goes through the first router, next router gets it, it decrements, hey, sorry, man, I killed your packet. Sends it back the other way, and I just keep incrementing it until I get all the way to the end. So it's actually a trick is how Traceroute works. We're eliciting the response from the routers along the way. Sometimes when we do a Traceroute, we see maybe 3 stars appear. And that occurs because somebody is either not sending those ICMP TTL exceeded messages, or they got blocked for some reason. That's generally not a good thing to do, but some network administrators block certain internet control message protocol packets. So when you're thinking about a network problem, I hope maybe you'll use this methodology of just draw out, go figure out what are the physical boxes that are in the way, and what happens to your packet as it goes through each one, and what did you put in your packet, and how does that packet change along the way. So we could do this again sometime. We could use IPv6. Somebody's mentioning CCNA. I always like to start with this whiteboard when I get new employees and they want to go get their Cisco certifications, all that stuff. I try to get them to think about routing and switching at a packet level. Because if you understand what has to happen, then you just have to go figure out how does each manufacturer implement this thing. That's just a matter of figuring out how do you configure their routing table, how do you configure their routing protocols. But if you understand what's going on big picture, you can always drill in and figure out the smaller pictures. So I think we're about out of time, but hopefully this made some sense to you. I'd be glad to go through and do it again. But I hope it was useful. So
this was absolutely fantastic, Dan. And I thank you on my own behalf and the communities. This is such a valuable resource. And so I don't, thank you. And you can see all the things.
Well, you're very welcome. Very welcome. So, and again, we can do a smaller lunch sometime, and we could even drill in and sort of have a more interactive session if you want to kind of ask questions and kind of drill into some things a little bit more. But
yeah, that would be great. And if folks have suggestions for what we can rope Dan into helping us learn next, just let me know. And with that, I think we'll call it a day, and thanks all, and hope you have awesome. A great rest of Monday.
Thanks, guys. Enjoyed it.
Thanks, Dana. Thanks, Dan.
Yeah. See you, Celeste.
Yep.